finished his PhD studies at Bernstein University. He worked for a short while in Apple, but in the past 2-3 years he worked as an architect in SambaNova. SambaNova is a company that develops AI processors. Thursday was his last day, so he's going to start soon at Speed Data, an Israeli company that I'm sure some of you knows. I like when I introduce speakers to tell something that's a little bit different that people don't really know about them. So Adi, in 2017, promised himself to run 2,017 miles. In kilometers, it's even more than 3,000 kilometers. And he ran it, and wow, that's an amazing thing, an amazing personal achievement.
Wow.
So Adi, please.
Thanks. Well, thanks for the kind introduction. Quick shout out for all the organizers for doing this, for inviting me and doing this whole great evening. It's really a pleasure and a privilege to be here. Okay, so today we're going to talk about recent developments in two fields, which is AI and processing hardware, how the two have advanced and kind of how they're coupled and drive each other in a sense. So let's begin. So AI is transformational, it's revolutionary. It is on the path of becoming a transformational force for trillion-dollar industries with a possibly infinite application space. So while there are a lot of possible applications out there, there are two main fields where you can see that AI already made a huge transformation. The first one is computer vision. It was traditionally driven by traditional software engineering and feature engineering techniques, and also some classic ML techniques like SVMs. Then in 2012, the AlexNet paper came and revitalized the idea of using convolutional neural networks for computer vision. And from that point on, convolutional neural networks have been sort of a basic block for many, and if not most, of the state-of-the-art computer vision models. The second field is natural language processing. It was driven by traditional software techniques like the ones that was used by IBM's Watson in 2011 that won the Watson, the Jeopardy game show. And it was also driven by other deep learning techniques like recurrent neural networks and LSTMs. Then in 2017, the Attention is All You Need paper came and introduced the idea of transformers. And from that point on, transformers became the baseline for all those all those state-of-the-art NLP models like the variants of BERTs and the GPT families and all that. So while there has been a lot of work in these two fields, we need to think about what was so transformational about these two works that made them so pivotal and so successful. If you look at those works, you can look at the abstract of those works, and both the AlexNet paper and the Attention is All You Need paper that introduced transformers, and you can see in the highlighted lines there that they both highlight the use of GPUs, specialized hardware called graphics processing units, or GPUs, to efficiently process their models. So we can infer that it was actually the presence of the availability of specialized hardware that actually made the difference, because it enables the authors and researchers develop more complex models that are able to process large amount of data and do it within reasonable time frames. So now that we know that hardware and specialized hardware like GPU is sort of a key enabler for AI, let's try to think about why is it so important and why people are doing hardware for AI. So the first reason is that timing is always important. In the past decade, the compute demands of AI has started skyrocketing, but it came in at an unfortunate time from the hardware's perspective, because right around that time, silicon technology stopped exponentially improving. You can look at traditionally, we spent decades from the 1980s to the 1990s, early 2000, by scaling up the frequency, and then when we reached the point where we are unable to do it due to power constraints, we started scaling up cores. So instead of having a single processing core that go fast, we would pack more cores in a single chip and just make them go, that were not going as fast. But around 2010, even that became impossible because the power per transistor stopped dropping. So when you're exponentially increasing your number of cores, you would need to exponentially spend more power, and that became unsustainable. So at that point, people say that we need to rethink our processing architecture, and that's why a lot of people hypothesize that specialization, meaning customizing your silicon, is the way forward. And why is that? From the hardware perspective, AI is very hardware friendly. It has a lot of the computational properties that actually made them a good target for specialization, for acceleration. They are highly parallel, meaning that there's a lot of computational operation that are done in parallel and independently on different portions of data. It has simple control flows, so it means that there's not a lot for the hardware to figure out at runtime. So the hardware can be fairly simple, and it's also dominated by a few mathematical operations. You know, compared to traditional processors like CPUs, you don't need a lot of sophisticated logic and decoding to support all types of mathematical operations. For example, if you have a convolutional network, you can say, okay, you have a bunch of multiply and accumulate, some exponents for your softmax, some max spooling, and that's kind of pretty much it. And you have all those activations, non-linear unit, but it's very confined in terms of domain. The second is that from the software frameworks perspective, AI software frameworks like TensorFlow, Keras, and PyTorch are very hardware friendly, meaning that the computation is divided to subblocks called tasks. Like you can see here, you have a bunch of convolutions, some normalization, some activation, and it's all very confined. There's abundance of parallelism, and then it's known in compile time. And also you can know how the data actually is being orchestrated and being communicated between the different blocks. And finally, you don't need to educate programmers and data scientists compared to imperative languages like C++. All the parallelism is done in the back, and you can have a magic compiler to do everything, because when they write AI programs, they're already educated. When you write an AI program, you're writing a hardware-friendly code already, and you don't need to go and change the interface and try to re-educate scientists. Finally, the reason why we're doing AI acceleration is there's pretty much no other choice to run AI in a relatively performant way. Back in 2013, Google did a study and tried to look at the trends in speech recognition, and they got to a conclusion using back of the envelope computation is that sometime in the future, if people are going to use only 3 minutes a day in speech recognition, we would have to double our data centers if we just kept them CPU-based, if we would stick to the traditional, inefficient, general-purpose CPUs. So at that point, they started working on their own in-house customized silicon, and in 2016, they deployed their own silicon named the Tensor Processing Unit. So the Tensor Processing Unit was, in 2016, I would say the largest scale deployment of a silicon-based architecture that was built from the ground up for the purpose of deep neural networks. So the AI landscape is rapidly growing. If in 2017 we had like a GPU, the TPU, and handful, occasionally a few CPUs, right around nowadays we have hundreds of corporations as startups. They're all developing different AI accelerators, AI silicons for different systems and different architectures. And the revenue from deep learning accelerators is expected to grow to dozens of billions of dollars annually. So while there's a huge solution space, I would say that there's a handful of solutions that it seems like a lot of the corporations are pursuing. So the first class is the good old GPUs, so like NVIDIA's GPUs. So they have massive parallelism, a lot of simple cores, simple control flow. The instructions operate independently on different portions of data. And because they have, I would say, because they were the gate openers, they have a head start compared to the other startups that are just starting. They have years of experience in mapping AI problems to GPU hardware. But someone would argue that GPUs are still too general purpose, so they're kind of bounded by the overall efficiency that they can give. And it's a little bit different from getting a software stack that was initially It was initially designed for graphics, and then it was repurposed a little bit for data science and for scientific application and doing it AI, versus having your own silicon that was built from the ground up only for the purpose of AI. That's why they started pursuing other directions. So the second class would be very long instruction word architectures, or VLIW. And in the center of it, there is this circuit called a systolic array. So examples for that are Google's TPU, Grok's TSPs, and Habana's Gaudi and Goya chips. So the idea is that you have a heterogeneous compute path composed of different units, for example, normalization units, a systolic array, maybe a transpose, and you have a compiler that looks at it and sees and basically generates instructions that are compound instructions. You can see an instruction that consists of a few sub-instructions. Each one of them is fed to the respective units. So it's able to save a lot from the instruction set, from the burden of instructions compared to traditional CPUs and also GPUs. The next one is a combination of reconfigurable architecture with data flow computing. Examples for that are SambaNova, wave computing, simple machines, and others. And the idea is that, first of all, data flow computing operates on the computational graph. So it's an inherently very, very parallel compared to traditional instruction-based models like also known as the von Neumann models that GPUs and CPUs are using. You're operating on the graph, and it's very natural from the AI perspective. And the second element is a reconfigurable architecture. You have your basic blocks of compute and memory, and from that you have a smart compiler that looks at them as almost like Lego blocks and tries to fuse them to create all sorts of different shapes and patterns to basically accommodate a lot of forms of compute. The idea is that it's really flexible, and by doing that, one of the main selling points of reconfigurability is that you can solve a really general set of problems but reach also high efficiency. Why do you want to be flexible? Is because it takes 2 or 3 years to make a chip. So you need to think about not only today's AI problems, you need to have a general enough stack to support the problems that will only come out 3 years from now. And that's why you need your architecture to be, I would say, long-sighted. Finally, the final class is processing in memory. So the idea of processing in memory, like Mythics and Neuroblades, is that a lot of the energy and time is spent not in doing computation, but actually moving the data around from the memory, doing the compute, and moving it back to the memory. A lot of it is spent on data movement. So these companies are making memory units with logic inside of them, and the computation is done in an analog way using basic circuit laws. And it's also known as neuromorphic computing, which you can say it's closer to the way that the brain operates, using sort of synapses and that. By doing that, doing everything inside the memory, you're able to save a lot of the costs. So now that everything seems fine and everything seems really promising and there are a lot of ideas, we need to think about the future of AI. What we can do better. So the first thing we need to do is kind of bridge this, I would say, this innovation gap between academia and industry. There are a lot of ideas, but if you look at those foundations in the literature, they all have existed, maybe even 50 years ago. They're decades old, so they're, I would say, the culminations of ideas that have already been out there. On the other hand, in the academic world, as you can see here, there are dozens of papers published in the top tier computer architecture papers every year. So there's a lot of innovation that we can still adapt and can still trickle down from the academic world into actually materialized products. The second challenge is we need to improve the way that we're benchmarking AI accelerators. Currently, there is this benchmark suite called MLPerf, which in my view has several shortcomings and issues that still need to be worked out. First of all, it has a few I would say less than a dozen applications. And while you're setting that as the industry standard, what it causes is some companies are overly specializing their architectures to these cases instead of becoming more general. So you have there's resonance and BERTs which perform pretty well, but when a data scientists come and try to implement it, they suddenly see that their performance is not really good. So we need our stacks to be more general and enable data science rather than kind of limiting to a few possible contrived cases. The second thing is that MLPerf apps are all based on papers that were implemented on GPUs. So all these papers, nodes and those structures and those hyperparameters, they're all really tuned to the way to everything that you can achieve using a GPU architecture. But right now there are hundreds of other solutions. So we need to think about, well, are these applications really what AI can do? If we had, for example, the TPU existed by the time we had GPUs, maybe the application space would have looked differently. And finally, we need a bigger emphasis on the way we're looking at compute efficiency. You can see claims that are saying, okay, we have MLPerf exceeding Moore's law. And when you think about it, you can think that MLPerf is when you as a data scientist, you're going to see like exponential or tenfold improvement over the years, but it's actually not. If you look at those works, these were achieved using hundreds of GPUs, and these were achieved like using 3,000 TPUs. So from a data scientist perspective, it would be pretty much impossible because the only people that can actually do it are the hyperscalers, the Googles and the Facebooks. So this really nice improvement in performance in MLPerf does not really affect the data scientist. And that's what it should actually do. Because the way I see it, what the main selling point of AI accelerators is that they were able to commoditize scale. Just having you as a data scientist develop bigger models and do it all within reasonable time frames. And the last point that I want to emphasize is that we need to make AI hardware really about AI. I interchangeably use AI hardware because it's catchy, but it's actually it's overstating what it actually does. So being a key enabler, hardware actually, we consciously scope and narrow our scope. So if you look at this figure from Ian Goodfellow's book, you can see that there's AI, inside of it there's machine learning and representation learning, and right around inside of it is deep learning. I would say that most of the AI accelerators that exist today are basically good at tensor-based computation, meaning everything that can fit in an n-dimensional, either matrices or vectors, and it's a kind of like a fixed size. So arguably you can say this covers, some portions of deep learning, a little bit of representation learning, and some ML. But we need to think about, is there more? Is attention all we need? Is convolutions all we need? Or do we need bigger, more diverse application space for future AI? Will that enable data scientists, or are we kind of converged to sort of a local minima? Well, if we would develop a different architecture, we would be able to cover more bases. Questions? Yeah. Yeah, I think that there are architectures you can see in industry for things that are not purely tensor-based, like models that are more irregular, I would say, more ML-like, something like graphs, for example, graph learning, things like that. There are, I would say, if you look back at these, for example, at these properties, they're not really well mapped to that. They have some irregularity because some node, if you look at like graphs, for example, you have some graphs that are connected to 10 nodes. You have several nodes that have like 10 edges, and you have other nodes that have millions and billions of edges. So you never know. There's high irregularity in the way that you're doing compute. That's something that I would say that current accelerators like GPUs and TPUs might not be able to master just as good.